I invite Ms. Srividya to introduce Dr. Mithun, scientist F from MRL. Srividya, please introduce, sir.
Yes, ma'am. So here is a brief introduction of Dr. Mithun Palitzer. Dr. Mithun Palitzer, currently working as Scientist F in Powder Processing Group and Advanced Magnetics Group, Defense Metallurgical Research Laboratory, DMRL, Kanchanbagh, Hyderabad, since 2003 till present. He pursued his PhD at Indian Institute of Science in Materials Engineering, Bangalore. Sir has over 65 papers published in refereed journals and presented over 100 national and international conferences. He is honored by many awards, like National Science Academy awarded Sir with Young Scientist Medal in 2014, and he's also honored and awarded as Young Metallurgist, DRDO Young Scientist, and many university medals and awards for his excellency. He is also elected member in Indian National Young Academy of Science and life member of Indian Institute of Metals Material Research Society of India and MSI. He is also a reviewer in many journals, some like Metallurgical and Materials Transaction A, Journal of Alloys and Compounds, Material Science and Engineering B, Material Characterization, Trans IIM, Physica B, and many. I feel glad to invite you, sir. Welcome. It's over to you, sir.
Thank you for the nice introduction, and I would like to thank the organizer for inviting me to deliver a lecture and share our work with this august audience. So may I now share my screen?
Yes, sir, you can share.
Okay. Yes, sir.
Yeah, is my slides visible?
Yes, sir, we can see.
Yeah. So good afternoon to all of you. So as I was introduced that I am coming from Defense Metallurgical Research Laboratory, which is one of the laboratory under DRDO umbrella. And we basically work for material development for many defense applications. And today I will be concentrating in this lecture about the smart magnetic materials. So the smart materials is a very jargon kind of in the recent times. And the cartoon, what I depict here, it shows an aircraft with a wing like a bird. So essentially the purpose of smart material is to make the system biomimic, as versatile as it is observed in the nature. However, the way the technology to realize such dream is so difficult. As you can see over here, this plane, what is shown here, it's just not so effective because the technologically the concept could not be integrated with the system. Well, when we are talking about smart material, so we are considering some material which respond to external stimulus in a specific manner. The stimulus can be like temperature, moisture, external stress, pH, electric or magnetic field. And in today's talk, primarily, although I will introduce the smart material at the beginning in a brief, but my focus will be whole and soul on the magnetic field induced smart materials. And these stimulus can, when we remove them and they come back to the previous state, as you can find this electric kettle over here, it has a thermostat, which basically when the the fluid inside it, the liquid inside it is completely heated, it switches off, cuts off the circuit, and once it cools down, again it comes back to its original position, and then it allows further heating. So not only always a smart material comes back to its shape, nowadays the definition of smart material also encompasses some smart behavior of a material under external stimuli. And when a smart material is exposed to external stimuli, the several changes can be noted. One is size, shape, state, like it can changes its phases from solid, liquid, or gas, viscosity, conductivity, and of course the magnetic properties. So here I classify the smart materials into three main categories. One of them is the thermally activated one. I will talk about brief, like polymorph, shape memory alloys, shape memory polymers, etc. And the magnetically or electrically activated, like magnetostrictive alloys, ferromagnetic shape memory, magnetocaloric materials, magnetoelectric materials, magnetorheological fluids, MR fluids, spintronics, and the piezoelectric materials. And of course, there are others which cannot be classified with neither temperature nor electric or magnetic field. And we will talk about little bit on that also. So I will before going into the magnetic field assisted smart material, I will briefly talk upon the other categories of smart material. To begin with, a polymorph, it's a kind of a biodegradable polymer, which is actually when you hit beyond 62 degrees centigrade, it becomes semi-solid or semi-liquid, whatever you can say. It's amenable for shaping, whatever shape you want to give. And then once it cools down, it becomes very rigid, machinable, and it can be actually cut by the straw and all these things. So this is particularly used not only for the rapid prototyping, also for the medicinal use like dentistry and some implantable devices. The second category is the temperature responsive polymers. So this basically changes its property once the temperature is changed. This can be used for the smart coffee mugs. When you pour the tea or coffee which is hot, it changes its color or appearance to give you an indication, to give the indication that the user that this is a hot condition, so they should be careful. And then it changes its appearance once it is comes back the room temperature. So this is also such a biomedical application, and also you can use for smart clothing. So you can see that if you are exposed to very high sun heat, then it will change its color or appearance. So the other category is smart gels. So these are the gels which can change its essentially the viscosity and the hydrophobicity or hydrophilicity under the influence of light, magnetic field, temperature, and so on. And this has the application for the drug release, organ replacement, and also some industrial applications like shock gels and the shock absorbers. The other category is thermochromic inks. This ink basically changes, similar to the other one what I described a few minutes back. It also changes its color. In fact, now you can basically a boiled egg, if you coat with this material, this ink, basically it will tell us when it is boiling that okay, the boiling is complete or not. The other category is thermocolor. It's also similar type of smart material which you can apply on the garments, and it will tell you that what kind of temperature it is, or you are close to a very hot zone, that how far, suppose there is a fire, there is a furnace which is on, you should not go very close to that. It will give an indication. So this has a very good application in industrial and the fire safety too. So there are other packaging smart material which has a sensor for sensing the chemical gases which emits from the ripened fruit. When the fruit gets ripened, the concentration of the gas molecule inside the pack, it changes, and the sensor can give you an indication that whether the fruit has ripened. Suppose you have purchased any so-called unripe fruit, so when it is purchased, when it is ripened, it can give you an indication. And also the other category is active packaging. Suppose you have to store a food for a long time. So this packaging material is so smart that it can absorb the oxygen or moisture and then reducing the growth of a bacteria, and thereby helps the material, helps the food not to perish so early. So now the other category of thermally activated material, SafeMat material, is a shape memory alloys. And shape memory alloys is a very interesting class of material which basically changes when you plastically deform the material, and then you are heat or cool based on the system, so it can recover its original shape. So shape memory alloy is also called pseudoelastic material, and the mechanism of the shape memory effect can be either through phase transformation or through movement of the twin boundary motion. So there are different thermal shape memory alloys like nitinol, copper zinc aluminum, and copper aluminum nickel. Of course, there are ferromagnetic shape memory alloys, which I will describe little later, and which is nickel, manganese, gallium. The shape memory alloys, they find a wide variety of application. It has aeronautical application for the flexible wings, and it has the bone implants you can made out of it, dental braces, stents for the arteries, and the memoflex plex. This specs actually, based on the temperature, it can basically tightly fits around the glasses, and then it will not be anytime loosened actually. And then bioengineering, you can basically make the muscles using shape memory polymers and so on. And shape memory polymers are similar to the shape memory alloys. It also has the phase transition temperature, need not be austenite to martensite, but some other type of order and disorder phase transformation. So by which it shows the shape memory effect. And this you can use for interesting application like non-iron clothing. Whenever you are washing the fabric due to the cold temperature, or in a washing machine, you can set a temperature wherein the cloth will attain that shape memory, that phase transformation temperature, and thereby what will happen, all the crease whatever is in your cloth, they will decrease, and the cloth need not be iron. There are also biodegradable surgical stitches you can make with these polymers, which will be basically closing the wound, and then it will be part of the body. And also for the small and medium scale unmanned aerial vehicle, you can use it mimicking a bird's wing, and this can be used for various applications with great flexibility. There's a phosphorescent pigments. Basically, it emits some light frequency under the external photonic stimulus, that is light stimulus. These can be used for some indication, than the traffic indicator at the many other places. The other material is the organic semiconductor, which basically emits the voltage under the external, the sunlight. So it can be used as the flexible solar cell, which you can use for our t-shirt or some garments, where we can use this solar signal and then generate some power, at least for the charging our mobile and other gadgets. These are all some organic material. And then I will come to the nanomaterials. Well, nanotechnology, I don't need to tell you, it's very well known, and it has got several applications due to its exotic properties and due to its high surface to volume ratio. And this is the pressure sensor, nanowire based, where it can sense pressure. Basically, there is if you connect an LED with this sensor, then based on the pressure applied, it produces a different voltage, and accordingly the intensity of the LED changes. So it can kind of sense the pressure. The other one is that tunable LED, this is nanorod. So basically gallium nitride, there are two semiconductors in between interfaced with the GaN5 nanofibers. Basically these nanofibers, you can gradually change the indium doping concentration from one end to other end, and accordingly you can tune, and using the same material you can produce the LEDs of the different photonic contrast or different color. The other one is the carbon nanotube. It is a very smart and exotic structural material. It has got very high tensile strength, unique electrical properties, and the heat conductance. It has got several applications such as waterproofing and also some sports equipment, and in some circuits, motors as conductive films, and there are several medical applications for the killing bacteria, drug delivery, and regenerating the damaged tissue. A similar class of materials are fullerenes. They are also used for various applications like armchair, zigzag, and chirals. And fullerenes are also used as superconductors, different medical applications, and also HIV protease inhibitor. So nanomaterials are exotic. It can be used for many other applications. For example, the planes and gliders, they use the higher strength to weight ratio, the nanomaterials, the cars, the windshield, they are used that which is basically hydrophobic material, which is not allowing the rain droplet to stick around the windscreen. And so they are all very fine nanofibers which are coated in the windscreen, and also another great application. However, nanoparticles comes with certain cautions and certain risk factors, like they can be dangerous to the our physical condition, our especially skin and lungs, and also for the bloodstream, unless we use proper cautions. And although some of the nanoparticles are routinely used in some cosmetics like sun creams and so on, however, they are not all the nanomaterials are very damaging, or but we have to take proper precaution to handle them. Then the other class of smart materials is hydrogels. They are used in nappies and sanitary towels, contact lenses, water release granules for the plants. They are basically hydrophilic material. They absorb a lot of water, especially whenever you have places with very less rainfall. There you can use these to sustainable agriculture development in those places. Now, the electrically stimulated smart material is the piezoelectric material. The piezoelectric effect is that whenever you are subjecting a material to some kind of mechanical stress, for example, in this picture, the strip of a piezo material is bent and then it produces some voltage. This voltage you can make use of something, and the inverse piezoelectric effect is that if you apply a voltage, for example in the strip, then it produces some stress, and by that it bends. So this you can use for some actuator sort of application. Now let us come to our core area of today's lecture, that is magnetic smart materials. So like other smart materials, the magnetic smart materials responds to external magnetic stimuli, that is magnetic field. So I will start with the magnetostrictive material because DMRL has done a considerable work in this field. So I will few of our work and results and revelations I will show to you today. So the magnetostrictive material is the ferromagnetic material which changes its dimension under the influence of the external magnetic field. A material can expand or a material can contract under the external magnetic field. So accordingly, it is termed as positive or negative magnetostrictive material. It is not only applicable in the bulk, it is also applicable in a thin film. For example, in this thin film, the top layer is magnetically active, bottom layer is magnetically inert. So if you have a positive magnetostrictive material, the film bends downwards, and because this is inert, this will try to accommodate the stress generated in this layer, so it will try to bend downwards. In case of a negative magnetostrictive material, the film will bend upward. Well, there are the different kind of magnetostrictive effect. One of the effect is called Joule effect, wherein the change in length is observed, and there is the reciprocal of Joule effect is called the Velary effect. So that means, like as I mentioned, in case of a piezoelectric material, if you apply the voltage, it produces stress, and if you apply the stress, it produces voltage. So the effect is vice versa. Therefore, here also in some of the material they are called piezomagnetic material. So the piezomagnetic material exhibit Velary effect, wherein if we apply the if you apply some stress in the material, so it will show the change in the susceptibility of the permeability of the material. So there are different magnetostrictive effects. Direct effects are Joule magnetostriction, which I described, delta E effect, where the change in the elastic modulus under the magnetic field is observed. Weidmann effect, the material produces a torque and it gets twisted under the influence of magnetic field. And Magneto-volume effect. In the Joule magnetostriction case, under the magnetic field, the volume remains constant. So means if the length changes, if the length increases, the diameter decreases. Whereas in case of the Magneto-volume effect, there is an overall change in the volume under the influence of external magnetic field. So Joule effect inverse effect is called Velary effect. Weidmann effects inverse effect is Matteucci effect, and Magneto-volume effect inverse effect is called Nagoko-Honda effect. Well, how the magnetostriction comes in a material. So this is the magnetic domains in a material which is above Curie temperature. They are randomly oriented. So therefore, when we just apply the magnetic field, when we just not even apply the magnetic field, I cool down the material below the Curie temperature. Basically, they will undergo some domain ordering, and in this process, it will show some finite amount of change in the length. So that is called the spontaneous magnetostriction. And over and above, if we apply some external field, it will show further elongation. So that is called positive magnetostriction or the forced magnetostriction. So the total magnetostriction in a material is a culmination of spontaneous magnetostriction plus the forced magnetostriction. Well, there are several applications of magnetostrictive material. So as a defense laboratory, we are working for applications like sonar, smart wing, mine detection system. Apart from that, there are many societal or civilian applications like surgical tools, hearing aid, fuel injectors, high force linear motors. It also used for the seismic detector, solid state speaker, and also vibration control system. I think several devices have come up with active vibration control system using the magnetostrictive material. So for the magnetostrictive thin film, it can be used for sensing the force as a force sensor, and also it can be used for the microprom to deliver a small volume of liquid in any MEMS devices. Especially for the cooling fluid of MEMS devices, you can, for the cooling fluid development, delivery system, we can use such microprom using a magnetostrictive thin films. So magnetostriction is measured using various methods. The most widely used method is the strain gauge method, where it is connected to a Wheatstone bridge, and the bridge unbalanced potential due to the change in the length of the the magnetostrictive alloy is measured. Apart from that, there are capacitance method, stress dependence hysteresis loop, SAMR method, and the transverse susceptibility method. So there are different type of magnetic smart material. So you can see that there are 3 magnetostrictive materials which shows a strain to the tune of up to maximum 0.2%, and you need actuation voltage less than 15 volt. Whereas for the ferromagnetic sub-memory alloy nickel manganese gallium, though the maximum strength can be realized in a single crystal is very high, up to 5%, but the actuation voltage required is very high, greater than 50 volt, which is certain disadvantage in making a device for a mobile platform. Nitinol, the sub-memory alloy, also gives very high strength, and it has got a very moderate voltage requirement. However, nitinol is a thermally activated system, so it has also always got some hysteresis. That means the temperature of phase transformation while heating and while cooling is not same. So therefore, every cycle the material will always left with some residual deformed material, deformed strain, and this deformed strain will slowly build up and decreasing the total cycle life of the material. And PZTs are very good, but PZTs also shows 0.1% strain. However, the voltage requirement as an actuator is very high, and this electroactive polymers also requires quite a bit of high voltage. Regarding the magnetostrictive material, there are different material. However, you can see that pure rare earth, dysprosium and terbium, they show very high value of these values are reported in ppm, that is parts per million. So 3800 and 2800 parts per million. And whereas these 2 materials, actually you can see it is written here at cryogenic temperature. So therefore it cannot be used for any practical purpose. However, if we make some intermetallic combining the transition metal like nickel, iron, and the rare earth material like dysprosium and terbium, because they have very high magnetostriction and they have very high Curie temperature. So combining them, if we can make an intermetallic, so we can realize decent amount of strain which is operable at ambient or above ambient temperature. So this, you can see that the rare earth material, due to their the source of magnetization from the 4f electron and spin orbit coupling, so they are all Curie temperatures is much below room room temperature, whereas transition metal has high Curie temperature, but they have very low spin orbit coupling. This spin orbit coupling is the D factor which controls the magnetostriction in a material. As usual, the rare earth having a large spin orbit coupling, they have high magnetostriction compared to transition metal. So therefore, combining them, we can find that if we take a ternary DyTb iron, so such material has a very good magnetostriction with Curie temperature above room temperature. This particular material is formed in a cubic structure with 111 as easy axis of magnetization. So that means the material needs to be or preferred to be oriented along this easy axis so that we can derive the maximum benefit of magnetostriction out of this material. So, and this material processing is quite a bit of challenging. As I was telling, that orientation is mandatory. Therefore, we have to impart some processing route such as unidirectional solidification to make the material oriented along the desired direction. So therefore, it is quite a challenging in the processing, and moreover, it contains a huge amount of rare earth, and rare earth is very reactive to the environment. So you have to handle the material very carefully under the inert condition. So and also this particular composition, as I was showing in this phase diagram, does not have any flexibility with respect to solid solubility. It has a kind of a line. So therefore, my composition selection should be very precise so that I don't end up with formation of much other secondary phases which will deteriorate the property of the alloy. So in our place, we prepare this material in the two different routes. One of the route is called the zone melting route. This is one of the way we are imparting the unidirectional solidification of the material. You can see here that the cast material is a two-phase structure. Due to the good cooling rate, high cooling rate during the solidification, the second phase disappears, and accordingly we can see the magnetostriction of the unidirectionally solidified material improve, and the magnetostriction value improves with increase of the rate of solidification. And then when we studied the extent of grain orientation, which is studied by a method called the X-ray pole figure, that is the texture, the preferred grain orientation of a material is called the texture, and the extent of texture is studied by a technique called X-ray pole figure. And the more that intensity contours are focused towards the center, that especially those reddish color which is shown in this legend, and so that orientation is the more stronger. We found as the growth rate is increasing, the extent of texture in the materials becomes stronger. Accordingly, we have realized a better material. You can see this picture. This kind of actuator or transducer rods have been realized in DMRL. And also, but this technique has a limitation. It cannot produce a very big rod. So we have resorted to another technique. And this furnace was indigenously designed by us at DMRL and fabricated by an Indian fabricator. And this machine, with that, we could achieve a magnetostriction value which is even better than the best reported international value in this material. And the Titrima USA, the company which is the sole producer of this magnetostrictive material in the world, so our values are even slightly better than the values reported by them. And here also we have done detailed microstructural and texture analysis, and then we could realize the big 30 mm dia, 100 mm length magnetostrictive rod. And then we did not stop over here. To understand the efficacy of our material, we also designed some kind of a transducer for producing the ultrasonic vibration, the sound wave, for our underwater navigation, underwater communication application. So there are two types of underwater transducer. One is flex tensional type, wherein this magnetostrictive active material will be sandwiched in this shell under the pressure, and the other one is Tonpils type, where a head mass and tail mass, the material will be sandwiched between them, and they will be pre-stressed to achieve very good property. And we attempted this non-pills type transducer, and I will see. So this is the schematic. So here, this is the material, magnetostrictive alloy, and by a spring-loaded mechanism, some pre-stress is created, and this is the AC coil, and this AC coil will produce the AC signal and AC magnetic field into the material, and accordingly, you will realize ultrasonic vibration from this material. And to facilitate the closure of the magnetic field completely through and through the rod, we have designed a magnetic circuit using the soft Amco iron and very highly pure iron, and then we have designed this transducer, and this is the transducer in the 3D, and this is the hardware, and it has various components. You can see that this is the, and also to make the we also have developed some permanent magnet which is resin bonded type to to make the bias field. I will come a little while later why the bias field is required. This is the AC coil, and this is the spring which is creating the that compressive force in the transducer material. Now this is a typical magnetostrictive plot. You can see that if I operate at a zero field, zero DC field, and over and above, if I apply a AC signal, so basically in positive cycle I will travel like this, and in the negative cycle I will travel like this. So therefore I will get 2 times frequency for a single frequency of the input AC signal, whereas that will increase my frequency. You can understand when I am sending a signal underwater, higher the frequency, attenuation is high. So accordingly, if higher the frequency I use, I will lose certain advantage in transmitting the signal underwater. Therefore, I should not operate at origin. I should create a bias so that the operating field shifts over here. So what we have did, we have differentiated this plot to understand where the slope is maximum, because higher the slope, higher will be its sensitivity, and the actuator thrust will be highest. And we have identified the point, and then we have custom designed the resin bonded magnet, because DMRL has a very well proven experience in the field of rare earth permanent magnet. So we could easily devise a perfect recipe for making this kind of resin bonded magnet with giving the particular field of 300 Oersted along the axis of the rod, and accordingly we have made this biasing magnet, and then we have applied a AC magnetic field 40 Oersted peak to peak, and then using a laser Doppler vibrometer we have characterized the transducer. So if this is the input and this is the output, and then you can see that another thing what we have done is that when the AC the frequency is changing, then the impedance of the material is also changing. So that also we have calculated, and then applied voltage also we have plotted accordingly, and then accordingly we have chosen the perfect resonance frequency to derive the maximum output from the transducer. So this is only with one rod, but one rod is not sufficient to deliver the correct amount of thrust or energy. Therefore, we have designed a multi-rod transducer following the similar concept, and this transducer was actually tested underwater devices in our sister laboratory NPOL at Kochi. So here we could really realize a low frequency transducer with 1.65 kilohertz resonance frequency, and with 177 decibel RE mu Pascal as the input power of 394 watts, and this is quite comparable with the imported transducer. So far they were using the piezoelectric material. However, we have piezoelectric material, as I told, it needs lot of input voltage. So here with less input voltage we could realize the similar performance. However, this material has such a disadvantage. It is brittle, it is reactive, it is high cost, because rare earths are controlled by China, and the market price is mostly determined by the Chinese authorities. And so therefore the market price is fluctuating, and the bias field can be further decreased so that we can use more thin and thinner magnet, miniature magnet to produce the such kind of bias field. So to one approach to reduce the brittleness, so that any shape we can carve out of this material is suitable alloying addition. So we have adopted different alloy. I'll not go into the details, but one thing I would say that yes, we could improve the ductility of the material, we could reduce the brittleness, but we have slightly lost in terms of the magnetostrictive material. So therefore, the performance, magnetostrictive property. So therefore, to undertake this challenge, especially for the actuator application, we thought it is better to identify an alternative material which is not having rare earth and which is having very sharp magnetostriction versus magnetic field curve. So accordingly, we have searched for different material, we have done different calculations and found out with iron gallium as one of the great alternative. This iron gallium material, it has got a very good ductility and also but much better ductility compared to RFE2 material. Of course, it is not a structural material. We cannot expect the ductility like a nickel-based superalloy or steel or aluminum alloy. And also it has got a lesser coercivity, so that you can see the initial slope of the curve. This galvanol material has a steeper slope, so it can be a better actuator material. And we have done this material, we have developed through arc melting route followed by several heat treatment. And what we found that adopting certain furnace cooling, that is, and the quenching. So after certain heat treatment at 1000 degrees C, if the material is suitably quenched, then it gives a better magnetostrictive performance than the slowly cooled material. We have also studied the reason for that using transmission microscopy. We can find certain ordered phases present in the slow cool material. Basically, they are damaging to the magnetostrictive performance of the material, whereas in case of the quench material, you don't find this superlative spot corresponding to the order phase, and accordingly, we have better magnetostrictive performance. And also we have analyzed how this phase transformation occurred in this material, and accordingly developed a material with 400 ppm and very steep slope of magnetostriction. So I'll not go into the detail of this for this audience. And then encouraged by our success story in the bulk material, we thought it is better to explore the material property in the thin film. And when we go to the thin film, the magnetism, the landscape becomes entirely different because of the very thin surfaces, lot of missing neighbors at the surface, missing neighboring atoms at the surface, and they create some kind of the special magnetic interactions amongst the neighboring atoms, and they produces a different type of magnetic anisotropy in a thin film. So, and also the other important factor because of the size is the demagnetizing field. If you see that a very long rod, the demagnetizing effect is very minimal. If I measure the magnetization along this H1 direction and H2 direction, the plot shows there is not much difference. Of course, there is a difference due to slight demagnetization. However, if I go in a thin film and I measure in this direction and that direction, you see how much difference I realize in the loop. So that is the demagnetization effect. So that will we have to cater when we are talking about thin film. And also there are other factors like thin film thickness is another important thing. So whenever the thickness is thin, the magnetic domains, they align like this. That is called the perpendicular anisotropy. And when the thickness is more, the magnetic domains aligns along the plane. That is called the in-plane anisotropy. So therefore, the surface versus volume plays an important role in case of the thin film. So we have prepared this magnetic thin film first through sputtering technique. And to do so, we have to first prepare the target. We have prepared in-house the target, and then using the sputtering technique where we have prepared this magnetic thin film. And this is a special measurement, optical measurement technique for the magnetostriction in the field. So you can see there is an optical camera, and the film is placed with a proper fixture between two magnetic pole pieces. And then you can see this schematic shows how we measure the deflection, and thus using a formula, the increase in the length of this thin film or deflection in the thin film using these optical devices. And we have optimized lot of sputtering parameters. And then finally we have seen that also we have explored the depositing thin film at different substrate temperature, starting from room temperature to 550 degrees C. You can see at the room temperature the contrast are not so much, whereas very island-like contrast you can see, and this is increasing as the temperature is increased. So basically in the fine thin film, the AFM picture also shows same. And these Corsa islands, they play very important role in the magnetic domain structure formation in the thin film. And also we can see over here, this is the XRD. You can see that that initially it was a very wide peak, and the peak sharpens as the temperature increases. Well, if you see the transmission micrograph, you can see that at the thinner sample, room temperature sample, where you can see that the very fine channels they form, whereas at higher temperature we can see that there is, and you can see this grain size, they're very fine, the spot shows over here, whereas very well formed bright spots form at the sample grown at higher temperature. And we can see that BCC iron phase, alpha iron phase forms. And this is the magnetization versus magnetic field plot of these things at different temperature. You can see that at the room temperature, we have a very large coercivity, and the coercivity decreases as the substrate temperature rises. And when we look at the magnetostriction, this is the, I can see this is the room temperature value, and this is the 550 degree centigrade value. The room temperature value is slightly better, and because of the less quantity of iron phases, whereas it is less in the high temperature substrate, where the iron phases form in the larger quantity. Well, this magnetostrictive material alone cannot be used as the some kind of sensor. So we have used a concept called magnetoelectric effect. So wherein basically you can produce a sandwich between a ferromagnetic material and a piezoelectric material. The ferromagnetic material, if we demonstrate magnetostriction, basically as it expands or contracts, it produces some stress on the piezoelectric material, and you can produce some voltage by that. Basically, you can use as a magnetic field sensor or something of similar application. So we can see over here that terphenol and some piezo composite. So terphenol is the TBDYFE material, works out to be the better. And then conventional magnetoelectric materials, they are made with iron, cobalt, silicon, boron, amorphous material as the ferromagnetic layer, and aluminum nitride as the piezo layer. And the performance of this material is not so good like the magnetostrictive and the piezo combination. So accordingly, we have collaborated with Siri Pilani for fabrication of the devices. And you can see over here, this is the top electrode. Beneath, we have a magnetostrictive layer, and also there is, and below we have a ferroelectric layer, and then there is a silicon oxide, and thermally grown silicon oxide, followed by the silicon wafer. So the Siri Pilani has a facility for this micro machining of silicon. So they have produced such a nice small cantilevers from a silicon wafer. And then we in DMRL, we have grown the iron gallium thin film over it, and then we have produced the cantilever devices. And this is the package, and this material, this package, you can see that there are the different length of cantilever. So each length of cantilever has a different resonance frequency. So therefore, it can sense the AC magnetic field of different frequency. So basically, we have produced a wide band AC magnetic field sensor. Well, from the magnetostrictive material and magnetoelectric material, let us come to another class of material, magnetogeological fluid. So here the external stimulus is electric and magnetic field. So basically it is a colloidal solution of a resin polymer with that ferromagnetic or magnetostrictive material. So we have to optimize their composition and the size of the particle, and it should have an optimum value of pervasivity. So when the magnetic field is not applied, so the material is fluid, very low viscosity. And whenever the magnetic field is applied, then what happens that the particles, they align in the direction of the magnetic field, and as a result the viscosity of they basically kind of freezes over here, and the viscosity of this fluid increases, and accordingly we can tune the viscosity, and then the moment you remove the field, it comes back again to the normal state. So this has a lot of application, especially vibration damper, and also it can be used as the brake fluid. You apply the magnetic field, basically it will clutch around a rotating component and stop its motions because viscosity will be very high, and then you can again remove the magnetic field so that the clutch can be released actually. So then the part can again freely move. Like the thermal shape memory, wherein the austenite to martensite is the mechanism of the shape memory effect. The other is the magnetic shape memory effect, wherein upon application of magnetic field, there will be a twin boundary movement as depicted in this picture, and due to that, you will see the moment you remove the field, again the twin boundary move back to the original position, and therefore your shape will recover. So this will give a shape memory effect. Nickel manganese gallium is one of the very important material, and people have reported up to 10% strain. However, the field application which is required to enact such twin boundary movement is very high. You can, however, reduce this further by making the proper single crystal, and in DMRL we are working on that, and basically it has got several application: actuator, linear motors, and smart wing. So this shape memory alloy has one more important thing. When we are working with such material, we have to remember the shape memory effect comes only when there is a transition, this magnetic transition, and this transition temperature should be close to room temperature. Otherwise it is of no use for any practical application. The other magnetic smart material is magnetic caloric material, which is used for the magnetic refrigeration. So basically, when a magnetic material changes its magnetic state from ferromagnetic to paramagnetic state, so because the ferromagnetic domains are oriented, entropy is less. Whenever it goes to paramagnetic, it becomes random, so entropy is high, and such change in entropy can be utilized for heat extraction from a hot body, and accordingly it can be used for the magnetic refrigeration. In DMRL, we have developed a material GD5Si2Ge2, which shows 22 joule per kg Kelvin, change in the entropy at about a 275 Kelvin temperature, and this is a quite excellent property. And we are trying to collaborate with some private industries to try make a magnetic refrigeration device out of it. The other important magnetic sensor material is magnetoresistance sensor. So here, so this material has a particular properties. Whenever a material you can apply, keep it in the direction of the field and measure the resistance and flow a current, and then you make the material perpendicular and then flow a current, measure the resistance, you will see there is a change in the resistance. So this resistance change is called magnetoresistance, and this magnetoresistance can be used for sensor application, also for magnetic information storage, because you can change the orientation of this magnetic domain, and then by changing by electric current, applying electric current from the outside and then measuring the resistance, so you can read it as 1 or 0. Well, the other thing is in this kind of in continuation of this magnetoresistive that memory devices. The spintronic devices is another important thing, where the spin of an electron can be utilized to make, to transmit the charge from one electrode to other, and this can be used in preference to the conventional electronics, because the polarized spin, whenever this is the B is the magnetic field. Under the influence of magnetic field, the electron will have different spin direction. It will persist in the different direction, and this can be used as the switches, spin transistor, spin valve, and all. So then, and what is the importance of the semiconductor photonics? It is very fast. It can make spin quantum devices, and you can miniaturize the computer, and you can see that this is the calculator, how many ways the spin configuration can change in a molecule, and accordingly you can, so many states you can use for data storage and the data reading. So it is basically a technological advances, and we are also working in DMRL to produce a multi-layer spintronic devices for memory and also for the magnetic field sensing application. Now, at the last part of my lecture, I will introduce you to a completely different and very novel concept of the magnetic smart material. In fact, a material which is not otherwise comes under magnetic smart material, you can make it smart by external electric stimuli. This is a very new concept, where the concept of a lithium ion battery is being utilized. In a lithium ion battery, the lithium ion goes inside this electrode and charge gets stored, and the similar material, if a magnetic material have such layered structure, have some octahedral or tetrahedral void where the lithium ion can be hosted, such material can be utilized for this purpose. So this is a material, an intermetallic, a cerium manganese 2 germanium 2. And this material, you can see that this blue curve, basically prior to insertion of lithium ion, it has got coercivity very less, around 2000 Oersted. And then the moment we charge it with a lithium ion, very tiny 0.1 mole fraction per mole of this compound. If we charge this material with that much lithium ion, you can see the mammoth jump in the coercivity to the almost 10,000 Oersted. That is 1 Tesla. So from 2000 to 10,000. You can see here, and then the moment you take away the lithium by reversing the potential, then it comes back to the original coercivity. So a medium coercivity material can be converted into a hard magnet, and then the hard magnet is again converted to a medium coercivity material. Such smartness you can use for any kind of switching or any kind of lifting application. And you see that it is not valid for only one cycle. We have cycled it for many times, and then you find that coercivity systematically changing from 2000 to 10,000 and back. And this is otherwise CMN2G2 cannot be classified under smart material. However, we could make it smart material with this kind of lithium ion battery concept. Similar, another material is copper nickel manganese SB, where the Curie temperature without doing any lithiation is around 350 Kelvin. Now you can see that when I put the lithium in this, that is black one is the starting material, and when we put the lithium, that is in the discharge condition, the red curve, and when we take out the lithium, that is the charge condition, the blue curve, you see that magnetic moment is increasing or decreasing. So this can be used as a memory, a 1-0 application. You put lithium, you call it as 0. You take away lithium, you call it as 1. So you can reversibly do it. We have done it reversibly. You can see it is almost changing the magnetic moment with cycles of lithiation and delithiation. Well, the another material is zinc manganese SB. So this is also, you can see the similar effect of, change in magnetization. But so that means this concept, this philosophy is valid for different materials. Only you have to do a correct selection of material which is amenable for the lithium ion insertion. The other concept we have utilized, we have taken some iron fluoride. If you see the magnetization plot, it is passing through the origin. So that indicates this is a paramagnetic material. And this paramagnetic material, when we made it to react with lithium ion, so what happens that it reduces the iron F2 to iron. You can see the orange layer around this FeF2 particle. And when the iron comes from the paramagnetic, the material becomes ferromagnetic. And then when you do the reverse reaction by reversing the potential, again that iron converted back to iron F2. However, our initial experimentation, we were not successful by 100%, but we optimized our reaction, processing condition, this charging condition, lithium lithiation condition, and then we could achieve perfect, that is paramagnetic to ferromagnetic back to paramagnetic. So this is also very smartness. You can see over the cycles how from almost zero magnetic moment it is giving some close to 75 EMU per gram and almost back to very less. So we could achieve this kind of reversible tuning. And you see the different concept you can use. The other concept to use is the cobalt nanoparticle. So normally this cobalt nanoparticle, it shows blocking behavior. So you can see this is the blocking behavior. It shows a blocking temperature around 50 Kelvin. But if you can produce some cobalt oxide, that is cobalt you can oxidize on the surface, cobalt oxide shell, then what happens that the blocking temperature, which was at 50 K, due to this cobalt oxide, which is antiferromagnetic, the blocking temperature comes to almost close to room temperature. You see that high resolution transmission micrograph, where you can see there are two layers. Core, it is basically cobalt nanoparticle and cobalt oxide in the cell. So we have devised a system and carried out the tuning experiment. However, here the reversibility is not as good as the, that what we achieved in the earlier system. However, some more work can be done to optimize this cobalt oxide formation and the reduction to do that. So with all this, we are also now trying to explore how the strain can be utilized. So it is not only the, the electric charge, the lithium ion or any other electricity. So we can also make use of the strain to, make the material smart or change the property of the material. This is one paper from the literature. You can see just it's a thin film. So where they have changed the substrate material from, they have systematically, they have grown a ferromagnetic iron rhodium film on a tungsten substrate, and the tungsten they have systematically doped with vanadium to change the lattice parameter and producing different strength level, stress level in the iron rhodium ferromagnetic layer. And you can see that how accordingly the magnetization changes, the plot, the nature of this hysteresis plot changes. So it is feasible. So you can do it either by putting a magnetic layer on a piezoelectric substrate and then strain the material by a controlled piezoelectricity in the substrate, or you can make a composite. And I would like to end my presentation with a hope for the future, that it's a concept that if we can basically, magnetocaloric material I described, they are operable only at a particular range. However, if we can devise a smart magnetocaloric material which is amenable to the electric field tuning, in that case, or by the strain tuning, in that case, by changing the electric stimulus or the applied strain, you can shift this transition temperatures, or you can shift this area of the applicable temperature range and get a wide temperature range magnetic refrigeration. But it needs innovations in product and system. And my dream is that if not any material, at least many materials, we will be able to convert, elevate them in the class of smart material. I thank the DRDO for financial support, Director General Naval Systems and Materials, Dr. Kamal, Dr. Madhusudan Reddy, our director, and I also thank two of my colleagues, Dr. Chelvane and Dr. Himalay, because some of the experiments have been carried out like them, and also Professor Han. I was there in his lab, and the electrochemical tuning experiments, it's a Karlsruhe, Germany, I have done there, and Professor Markandelu, so he has offered his joint melting facility of IIT Chennai, and also the different group, electron microscopy group, structural failure analysis group, and chemistry group of DMRL for the technical support. And with this, I thanks to all of you for your patient hearing. And also, once again, I thank organizer for giving me the opportunity to present our work in this forum.
Thank you, sir.
Yeah.
Sir, there's some echo is coming. Just tell me. So thank you, sir, for enlightening us on smart magnetic materials. This talk certainly helped the faculty and the research scholars further in their research work, and this will becomes as a gateway, new gateway for some participants also. So they may start their research work in this smart magnetic materials. Thank you, sir, once again. And the floor is open for question and answers. Please, participants.
To add to your comments, I would also request the faculty members or the researchers for any kind of research collaboration with DMRL, please approach us. We will see that appropriate, researcher who is doing that kind of research. We'll try to have collaboration, and that way we can mutually, benefit and grow each other actually.
Yes, sir. Thank you, sir. Thank you for participants. Please. Either you can ask in the chat box also, you can put your queries in the chat box also, so that I can read out the questionnaire to the participants. Sir, I think people are might be they're sleeping, or might be they're not having any questions. They are thoroughly understood the talk.
Yeah, or maybe I am not. I was not so.
Following, no, it's not a problem for that. Sir, lastly, you said no that some are smart materials where we can change that ferromagnetic, like magnetic field.
Yeah.
Is it completely reversible, like kind of meteorological fluids?
Yeah. Maybe I will share back my things once again. So you can see that this results. For example, you see this one. So a material, you see that they are in a different cycles. So that means we have not taken out the material. It was done in a squid magnetometer, the entire experiment. So basically what we did, that entire electrochemical cell in a miniaturized form, we have prepared and inserted in the squid magnetometer. And then the magnetic measurement was carried out continuously over the cycles. This is a few days continuously, this was running actually. So you can see that when we are reducing the iron fluoride to iron by lithium ion, so the magnetic moment increases. And then whenever I am reversing the potential, then it comes back to iron fluoride once again. And then the next cycle, again, the same thing is happening. So they are completely reversible. Only one case, this cobalt nanoparticle, because of such a fine size, we could not control so reversibly. But otherwise, if you see the other results, like this one, for example, that change in the magnetic moment, you can see that this is almost reversible, where several cycles actually. Similarly, this one, that coercivity change, yeah. This one, you see this plot over here. So this plot also, you can see that over several cycles, this coercivity is changing, going up and going down with, lithium insertion and lithium taking away from the cell.
Okay. So is there any, don't have any effect on coercivity, sir?
Sorry. Yeah, I mean, actually, I did not tell you in the detail what is happening. So maybe now it's the time I can briefly explain. So basically, as I was mentioning, this unit cell structure is a layered type. You can see a lot of gap. This wherein this this lithium ion can go inside. You can see over here. And then we were wondering, actually, truly speaking, when the first time we got this result, then Professor Han was telling, oh, I think this you got it out of accident, or it's not possible, simply. I mean, anybody would say that, actually. So we repeated 2-3 times, actually. Okay, we are getting the same result. Then we were wondering, like, what is, and also it is reversible over the cycle, how it is. Then we took help of our DFT group, actually, and this they have basically made this band structure of this compound, and we can see here that this is the Fermi level, that thick line, sorry, this dotted line. And then what happens that initially it was over here, that thick line, and whenever I am putting lithium, so lithium is lithium plus. So lithium plus always come with the equal mole of electron. Otherwise, how the charge neutrality will be maintained inside a solid material? So that electron, when extra mole of electron is coming, so that basically increases the Fermi level from this thick line to the blue dotted line. And now once this Fermi level goes over here, then there are some cerium band. In this cerium band, some electron is going. And this electron is basically responsible for very high coercivity, actually. So that is how we arrived at. And then once you take away this electron, again this band is empty, and again the coercivity decreases. It is like that.
So thank you, sir. So it's almost a kind of a piezoelectric kind of material.
It's not showing any trend, but it is it's a unique. I don't know what category I should tell. It's basically kind of that material with tunable magnetic performance, I would say.
Yes, yes. Thank you, sir. Thank you very much, sir. So
Okay,
participants,
thanks.
please. Sir, there are no questions from their side.
Okay. Okay, fine. Okay, nice.
Then,
I will be happy to interact with some of you at least, or maybe my colleagues, if not me, always. Yeah.
Sir, my name is Saraswati.
Any questions from participants? So, participants, any questions you can ask, sir. Actually, most of the participants are from mechanical engineering background, sir.
I understand. Yeah.
So this subject
maybe
is very new
at
to
least they learned about different. I hope they got the information.
Participants, if you have any questions, please ask or type in the chat box. Sir, thank you very much, sir, for this.
Okay. So thank you. So then I will leave the thing. So with your permission.
Yes, sir.
Can
Sir,
I-
thank you very much, sir, for your very informative session, sir. I thought
Thank
mostly
you.
the participants are from mechanical engineering background, sir.
I understand. I understand.
So maybe
Yeah.
the subject is very new to them.
Yeah. So at
Please,
least I thought they will know about different smart material, and if they want to pursue any one of them, maybe if it is possible to help by us, we will help. Actually, it's like,
yes, sir.
Uh,
I think
two
our
things-
FDP on
two
is
things
only
I
on
would like
preliminary
to
or
say,
elementary
madam.
knowledge on novel material.
Two things I would like to say, madam. To
Yes, sir.
this
Sir, sure, sir.
myself,
You can.
Kandaswamy from MBSR Engineering College. Point number one, the speaker's voice was very scintillating and mesmerizing, and we are glued to the system. It was one thing, sir. Next is many applications you have shown has enlightened us. Smart material applications has enlightened us. We could understand what is the background of all such things which is happening at the back. Very interesting. Thank you.
You can.
okay. In that case, if there is no
Anyone want to give feedback? Please switch on your videos when you want to give the feedback or ask any questions. Sir, thank you, sir.
Okay. Thank you
Sir,
so much.
the session was very informative and it will be very helpful for us, sir. Sir, thank you for your talk, sir.